Hello everyone, my name is Ding Jie. My report title is Research Progress in Catalytic Conversion of Oxalate and Carbon Dioxide. I am from School of Chemistry and Chemical Engineering, Nanjing University of Science and Technology. My report is divided into two parts. The first one is catalytic conversion of oxalate. Point 1. Catalytic hydrogenation of diethyl oxalate to ethyl glycolate. Ethyl glycolate is very important because it can be used in synthesis of polyester fiber, synthetic resin, synthetic rubber, and so on. A silver-manganese composite catalyst was constructed in which silver atoms hybridized with a holodide-type manganese dioxide, resulting in electron vacancies in the inner layer of silver atoms, leading to surface electron transfer of manganese atoms and improving the adsorption of DeO on manganese sites. In silver-manganese composite catalysis, silver atoms undergo D2sp hybridization and the d orbital electrons of silver atoms undergo transitions, promoting the vacancy of d orbitals and enhancing the adsorption activation of hydrogen. The activated DeO reacts with hydrogen to generate ethyl glycolate. The number of active sites on the catalyst surface increases, the activation energy decreases, and the reaction conversion reaches over 99%. The selectivity of ethyl glycolate is improved to over 85%. The second part is catalytic conversion of carbon dioxide. Point 1. Thermal catalytic hydrogenation of carbon dioxide to produce short-chain olefins based on the characteristics of oxygen-rich vacancies on the surface of zirconia. An iron cobalt potassium zirconia catalyst was constructed on the basis of traditional iron cobalt potassium catalysis. The number of surface oxygen vacancies increased significantly, and the thermal stability of surface hydrogen groups was greatly improved. The electron deficiency of oxygen vacancies on the surface of iron cobalt potassium zirconium catalysis and their electron migration characteristics promote the affinity of the catalyst surface for carbon dioxide. The enhancement of carbon dioxide affinity on the catalyst surface promotes the adsorption and dissociation of carbon dioxide on the catalyst surface, generating important carbon monoxide intermediates and promoting catalytic reaction activity. The introduction of supple 13-4 breaks the directional growth of iron-copper potassium catalysis, promotes the dispersion of iron-copper potassium particles, and exposes the active crystal plane of copper-iron alloy or copper-iron 100 plane. The strong interactions between iron-copper potassium and supple 13-4 promotes the reduction of iron copper potassium, and the adsorption and dissociation of carbon dioxide on the surface are enhanced. Theta carbide iron active sites increased. Analyzing the transfer mechanism of hydrocarbons between iron copper potassium and supple 13-4, long-chain hydrocarbons formed on iron copper potassium mainly enter SAPO 13-4 through diffusion and are catalytically corrected into short-chain hydrocarbons. Based on the above research, a cascade two-step carbon dioxide catalytic hydrogenation mechanism was constructed to prepare short-chain olefins, greatly promoting the generation of short-chain olefins. Point 2. Photocatalytic carbon dioxide hydrogenation into methanol. The construction of carbon nitrate MRF forms a good chemical bond connection between the two components, and carbon nitrate has good photo-generated electron ability. This structure promotes 16.7% of electrons to flow directly into the MRF. In the carbon nitrate MRF core shell structure catalyst, the potential difference between the two components leads to the directed flow of electrons, which in turn promotes the concentration of amino group electrons on the MRF, increases the alkalinity of amino groups, and promotes the absorption and activation of carbon dioxide. In the carbon nitrate MRF core shell structure catalyst, carbon nitrate has good hydrophility and is easy to decompose water to obtain electrons. The influence of pi electron conjunction results in a more stable intermediate for carbon dioxide to evolve into methanol with increased activity. Based on the thermal migration characteristics of silver, silver is directed into the lattice pores of holodite type manganese oxide, while indium oxide is loaded on the catalyst surface, achieving the separation of hydrogen overflow active centers and carbon dioxide activation centers. The separation of hydrogen overflow active center and carbon dioxide activation center achieves controllable hydrogen overflow, promotes the generation of partially reduced indium oxide, significantly increases oxygen vacancies, and intensifies carbon dioxide activations. Silver atoms enter holodite type manganese oxide, and the oxygen in silver atoms and manganese oxide undergoes D2sp hybridization. The d orbital electrons of silver atoms are vacuumed by 1.7%, and the absorption activation of hydrogen is enhanced. Based on the strong hydrogen overflow characteristics of pyridium atoms, a series of enhancing interface oxygen vacancies and enhancing carbon dioxide activation by pyridium atoms has been constructed, providing a new approach for the catalytic conversion of carbon dioxide to methanol. A copper zirconia-supported highly dispersed pyridium catalyst was constructed by impregnation, loading, and ion exchange methods, which significantly promoted the activation of hydrogen and carbon dioxide, and significantly improved the reaction activity. The interface catalytic reaction mechanism between copper zirconia loaded highly dispersed pyridium catalyst and cobalt-based catalyst was analyzed, and a large number of positive ion clusters were generated at the interface, significantly promoting carbon dioxide absorption activation and thus enhancing activity. The above is my report. Thank you very much for listening.